In this lecture, we will look at the second type of mismatch called random mismatch. So we will first start off with an example device of a capacitor. So let us say that the capacitor has a certain width and length. Basically I am showing the top view of the capacitor. So this is the top plate of the capacitor, and of course the capacitance value depends on the area. Now it turns out that if you actually zoom into the edges, what you will find is that the edges at some level are not going to be completely regular, and there is going to be some small variation, and of course this variation will be completely random. So in fact, one of the things that sets apart random mismatch from systematic mismatch is the fact that there is some statistical distribution. So there is some statistical dependence of all or many circuit parameters. Now let's come back to this example. Because this value now, or rather this capacitor now has some variation in its edge at some microscopic level, you can talk about a nominal value of capacitance which depends on the area of the plate. So the nominal C norm is proportional to W times L, but the actual value of the capacitance will be slightly different depending on the distribution of these defects. So therefore you now need to find a way to figure out how this is going to affect you. So let me say that there is going to be some L plus delta L here. So I'll show that in blue. And this is going to have W plus delta W. And in other words, if I take two of these devices, two capacitors, maybe on the same IC or across ICs, I will find that this value of delta W and delta L has a certain distribution. And this particular distribution, right, will most probably be will have a Gaussian distribution, but one particular device capacitor may have a particular value of delta W and delta L. If I take a different device, I could have a completely different value. Now I need to find out a way to minimize this value of delta L and delta W. It turns out if you just do a statistical analysis of this particular structure, for example, you could slice this into very small strips either in the vertical direction or the horizontal direction. You will find that the value, when you increase the value of the width, in other words, let us say you don't do anything to the length and you increase the value of the width, it turns out there is some type of averaging effect on both delta W and delta L. So it turns out that if you do this, delta W by W and delta L by L both decrease. Similarly, you will see the same effect if you increase the value of the length of the plate also, right? So this means, of course, that if you want to reduce the relative value of delta W and delta L, you have to make sure that the area of the plate is as large as possible. Now in some cases this is obviously not easily possible, because now you need to find some way to compensate for the increased value of the capacitance. Now I will write that down as maybe three points. The first point is, if you want to reduce the random mismatch, you use devices with large area. Now I have taken the example of a capacitor, but the same is true for a transistor or a resistor or other types of components also. Now the second thing I wanted to point out, there is a process dependent effect. What do I mean by this? Of course, this is due to microscopic irregularities in the edges. If I do a more finely controlled process, or maybe in a different way, I may find that delta L by L and delta W by W is already smaller to begin with, right? So a better process can give you a a tighter distribution of the random mismatch component. And finally, it is possible to use circuit techniques to mitigate mismatch, random mismatch. Now, you will find that these kinds of effects are much more or magnified when you start looking at a class of circuits called differential circuits. Now when we come to those kind of circuits, we will study the mismatch of the differential circuit. For now, we will just take the example of a common source amplifier. Now I will assume that the common source amplifier has a resistive load, some resistor R. The input has some bias VB1. Let us say this resistor is RD and the value of the supply voltage is VDD. Now what are the parameters that can vary here? The parameters that can vary are the following. If I look simply at low frequencies and I am doing, in fact, let us go one step further and say I am only going to look at the DC bias point of this circuit. You will find that you could have random variation in RD. Okay, so you can represent that by some delta RD which has a zero mean and some Gaussian distribution. You could have a change in the threshold voltage of the device. So you might have some delta VT in the device. You expect a threshold voltage of, let us say, 500 millivolts. The actual threshold voltage of the device may actually be 490 millivolts or 510 millivolts. Apart from these two, you may also have an error in, for example, the capacitances associated with the circuit, but we will not look at that. You may also have an error in the mu and Cox value. So let us now write down the expression for the nominal value and the distribution around this. But the point is, you will represent those things in terms of certain standard parameters. So those standard parameters would be the sigma of the Vt. All of these, remember, will have a process dependent parameter. Now I am going to call that AVT in this case, and it should be noted that they are inversely proportional to the square root of the area. The sigma is inversely proportional to the square root of the area. Sigma squared will be proportional to the inverse of the area itself. Sigma mu n Cox. Again, you can represent that in terms of this parameter, A mu n Cox. The variation of resistors and capacitors is usually represented in a relative manner. So remember that the units of AVT, A mu n Cox, etc. may not be the same. So this would be AR over root of W times L. And finally, if you had a capacitance, this would be AC over root of W times L. What is the effect of having mismatch? Before we do the example, let us quickly cover that. The effect of having a mismatch on any circuit. So let us represent that by a two-port circuit, by a two-port network. It turns out that this effect can be clubbed very similar to noise as a combination of two sets of variables, a series voltage and a shunt current. And I'm going to call that some VOS and IOS. Now remember that if I take a particular circuit, it may have a particular value of VOS and IOS. I need to take a large number of circuits. Depending on the variation of threshold voltages, resistances, etc., I will see a particular value of input referred offsets VOS and IOS. So VOS is called the input referred offset voltage. And IOS is the input referred offset current. Please note that since we are talking about statistical quantities, it is quite possible for VOS and IOS to be correlated. I only say may because it is also possible for them to be completely uncorrelated. So it is possible for them to be wholly or partially correlated. And of course, because we are now dealing with statistical quantities, if uncorrelated, or rather for uncorrelated quantities, you need to use squared quantities in your analysis. In other words, if two quantities, if you are trying to find the offset voltage due to a random mismatch or a random variation in the resistance and a transistor VT, these two would move independently, and therefore you need to operate in terms of squared quantities. Now let us go back to do our example. We will do an example of a current mirror circuit. So let us say I am going to take a current mirror and analyze its output current for mismatch. So this is my input transistor, and ideally my output current should be I0, assuming that M1 and M2 are identical. Now what I'm going to do is I'm going to assume variation in certain parameters. For the purposes of this particular example, I am going to assume that there is mismatch only in the threshold voltage of the two devices. So let us say this device has a threshold voltage Vt and M2 has a threshold voltage which is Vt plus delta Vt. Now the minute I do this, the first thing I know is that both the devices have the same gate source voltages purely by applying KVL around this loop. So what I know is VGS1 is the same as VGS2. But now because the threshold voltages are different, there will be a mismatch in the output current. So I'll now say that the output current is some I naught plus delta I. I need to find out the distribution of delta I in terms of the distribution of delta Vt. If you do that for this particular circuit, your job is done. So how do I find out the value of delta I? So the first thing I can do is assume that this delta Vt is small. Obviously, nominally the two devices better be identical, and therefore any distribution is fairly tightly controlled. So I can assume that delta Vt is small. So that is the other assumption I am going to make. Once I do this, it should be now pretty straightforward, because now delta Vt or rather delta Vt is going to cause a change in delta I. So maybe if I write down the equations, it will be a little bit clearer before I write down the final quantity. So I know this is the basic expression. I know that dou ID by dou VGS is the transconductance of the MOSFET, which is GM. But in this particular case, I need to find out dou ID by dou VT. Now looking at the equation, it should be clear to you that this is the negative of dou ID by dou VGS, which is minus GM. Therefore, I can say that for small delta Vt, the change in output current delta I should be equal to minus Gm times delta Vt. Now what does this negative sign mean for us? What this is telling us is that if M2 has a larger threshold voltage, for the same VGS, its current will be smaller. In other words, delta I will be negative. If delta Vt is positive, delta I will be negative, and vice versa. So that is what that negative sign is telling us. This is well and good, but this is for a particular device, for a particular value of delta Vt. I now need to find out what the distribution of the delta I is. So to do that, I first need to find out the relative value of this. So I need to find out delta I by I naught. So for a given value of bias current, what is the distribution of delta I? This is of course minus Gm delta Vt by I naught. And so let me rearrange this to once I know this, what I actually want to find is the distribution. Okay, so I am going to find out sigma squared delta I by I naught. This is actually what I want. I want to find out either the standard deviation or the variance, so that I can find out how tight the distribution is of the output current relative to I naught, of course. So this sigma squared delta I by I naught is now going to be Gm squared by I naught squared times sigma squared Vt. And now what is sigma squared Vt? This is nothing but Gm squared by I naught squared times AVT squared over W times N. Now this is telling us that for a given AVT in a particular process, if you increase the area, the relative value, if you increase the area of the device, the relative effect on delta I becomes smaller. For a larger bias current, this effect becomes smaller, and so on, right? Please also note that you have actually lost the sign, the negative sign that you originally had. That is because once you look at the tightness of the distribution itself, the actual dependence of delta I on delta Vt no longer matters. What you really care about are the mean and variance of the Gaussian distribution itself. At that point, you do not care about this particular negative sign.